Welcome to the 21st lecture of combinatorics. So, in the last class we were considering this problem, namely x1 plus x2 plus x3 plus x4 equal to 18, and we want to find the integral solutions of the equation, but there is a constraint for each variable. X1 is in between 1 and 5, x2 is in between minus 2 and 4, x3 is in between 0 and 5, and x4 is in between 3 and 9. So, how will we solve this thing? What we should notice, so the kind of form we described in the earlier formulation was something like this. Each xi has to be in between 0 and some ni. Then we will, after that we will use inclusion-exclusion principle and solve, right. But then in this problem even this form is not there. So, for first is between 1 and 5, second variable is in between minus 2 and 4. So, we have to make the work on the lower bound for each variable first, right. We should make each of them 0. So, what we can do is we can replace x1 by a variable y1, right, which goes from 0 to 5. So, what we do first is we replace x1 by a variable y1, but then y1 will be equal to x1 minus 1, because our x1 is in the range 1 and 5, between 1 and 5. So, y1 will be in the range 0 and 4, right, 1 less than x1. Similarly, x2 as given in the problem is in the range minus 2 and 4, minus 2, see x2 is in between minus 2 and 4. So, now we replace x2 by a variable y2, which is x2 plus 2. Then what happens is y2 will be in the range 0, because minus 2 plus 2 is 0, and 6. Whatever is x2, we add 2 to it, we create another variable which ranges between 0 and 6, right. Similarly, so that is next x3 is in between 0 and 5, x3 is in between 0 and 5, that is fine, and x4 is in between 3 and 9. So, x4 is in between 3 and 9. So, we will introduce y4, which will be x4 minus 3. So, that y4 will range between 0 and 6, right. Now, we can write our equation. So, this was our equation x1 plus x2 plus x3 plus x4 is equal to 18, right, 18. So, that we will rewrite as y1 plus, so I will use a different color, y1 plus y2 plus so this was 3, y3 plus y4 equal to something. What is this? So, the change is that y1 was x1 minus 1, y2 was x2 plus 2, y3 was x3 only, and y4 is x3 minus 3, sorry x4, y4 is x4 minus 3, you can just check it here. So, y2 we defined x2 plus 2, y1 we defined as x1 minus 1, and x3 and y3 are same, we did not change x3, y4 is x4 minus 3, right. So how will it change when we add this thing? So see x1, this thing is x1, x2, x3, x4 is adding to 18. So x1 minus 1, x2 plus 2 and x3 and x4 minus 3 will add up to minus 2 plus 2, total 16, right? 16. What we do is 18, this minus 1 will make it 17, then plus 19, and this will become make it 16, right? This is the corresponding equation. So formally we say that the solutions of this and solutions of this, right, with the corresponding constraints. Of case when I say x1 is in between 1 and 4, I am telling that y1 is in between when I am saying that x1 is in between 1 and 5, I am saying that y1 is in between 0 and 4. When I am saying that x2 is in between minus 2 and 4, I am saying that y2 is in between 2 and 6. Like that I am changing, and the range of x3 and y3 is same, and the range of x4 was between 3 and 9, but y4 will be between 0 and 6. And our claim is that any solution, integral solution of y1, y2, y3, y4, or in other words the set of integral solutions of this second equation, this is second, this is first, right, the first equation maybe, and second equation will have a bijection with the set of solutions of the first equation. So that is easy to see. I won't go very elaborately on because I have to cover a lot of other things. So what we do is you just have to notice that. So you get any solution here for this first equation, then what you can do is take the value of x1 in that solution and then minus 1 from that and assign it to that that value of x1 minus 1 you assign to y1, and whatever value of x2 is there in a solution we add 2 to it and assign it to y2, and similarly whatever value of x3 is in the part of the solution, as part of the solution x3, whatever value x3 gets, we will give the same value to y3, and similarly whatever value x4 gets, we will minus 3 from that value and give it to y4. Clear that it's clear that they add up to, now the values of y1, y2, y3, y4 add up to 16. So it is a solution for this second equation, and also it's clear that the way we have reduced the values, the range will be correct because x1 was in a certain range between 1 and 5. Now when you minus 1, it can, lowest it can go is 0, and the biggest it can go is 5 minus 1, 4, right. So it will come in the corresponding range of y1. So similarly the reverse also, for instance if I get a solution for y1 plus y2 plus y3 plus y4 equals 16, namely the second equation, then we can cook up the corresponding solution for the first equation. For instance, you will take the value of y1, add 1 to it and give it to x1. Similarly you will take the value of y2 and minus 2 from it and give it to x2, and similarly the value of y3 will be given directly to x3 and value of y3 plus 3 will be given to x4, and it's easy to check that the corresponding, if you add up now the x1, x2, x3, x4, so you will get 18, and definitely the ranges will be correct. So there is a bijection between the set of solutions of the first equation and the second equation respecting the corresponding constraints. That means we just have to deal with the second equation. So we have to worry about the second equation only, right. So now we can write the second equation. So this is the second equation. Yeah, this is y1 plus y2 plus y3 plus y4 equal to 16 is the second equation. The constraints are y1 is in the range 0 to 4 and y2 is in the range 0 to 6 and y3 is in the range whatever is given to x1, right, that is 0 to 5, and y4 is in the range 0 to 6, right. Each equation, each variable has a certain range. Now the good thing is the lower limit for each variable is 0. Here see, lower limit is 0. Lower limit for each variable is 0. So we are finding the form correct now. This n1 is equal to 4, n2 is equal to 6, n3 equal to 5, n4 is equal to 6. Lower limit is 6. So not that the corresponding R combination problem is that we want to create 16 combinations using objects from a multiset containing 4 type of things, where the first type has 4 copies in the multiset. That means you can only take that first type 4 times, and the second type has only 6 copies, and third type has only 5 copies, and fourth type has only 6 copies, right. So this is the corresponding R combination problem. The corresponding balls and boxes problem is that we have 16 identical balls. So we want to place them into label boxes: first box, second box, third box, and fourth box. The first box can hold only at most 4 balls. The second box can hold only at most 6 balls, and the third box can hold at most 5 balls, and the fourth box can hold only at most 6 balls. How many ways you can distribute 16 identical balls into these 4 labeled boxes with these constraints? This is the corresponding balls and bins question. Okay, anyway, we can try to solve it here. Now the next step is to use the inclusion-exclusion idea. So how will you do? So first you define the universe as the set of solutions of this equation, which we called equation 2, right, without these upper limits. That means y1 is at least 0, no upper bound on it. Similarly, y2 is at least 0, no upper bound on it. y3 is at least 0, no upper bound on it, and y4 is at least 0, no upper bound. In that case, we know the number of solutions, namely we can use the r plus k minus 1 choose r formula, where k is the number of variables, namely this is 16 plus 4 minus 1 choose 16, namely that is 19 choose 16. This is the total number of solutions of this thing without the upper restrictions. So this will be the universe. These solutions will form the universe. U will correspond to that. 19 choose 16, right. Now we will define the undesirable properties as usual. Undesirable properties. What is the, so there are 4 variables. We will, corresponding to the 4 variables, we define 4 undesirable properties: P2, P3, and P4. So undesirable properties are P1, P2, P3, P4. Which are the undesirable property? First undesirable property correspond to the first variable y1. That undesirable property says y1 takes values at least 5, means because here we are saying that desirable thing is at most 4. So the undesirable thing is at least 5. y1 is greater than equal to 5 is the first undesirable property. Second undesirable property concerned with y2. y2 is greater than equal to, here at most 6 is allowed, so at least 7 is undesirable. y3, what is the undesirable thing? Undesirable thing is it's at least 6, because we are allowing only at most 5, at least 6. And y4, the undesirable property is at least 7, right. These are the undesirable properties. Now we have to find the set A1, which is the set of solutions from the universe which has the undesirable property P1. Similarly, we want to find A2, the set of solutions from the universe which has the undesirable property P2, and similarly A3 and A4. We can look at what is A1. A1 means y1 is greater than equal to 5. A1 is only that we have y1 greater than equal to 5. For conditions on y2, y3, y4 is just that it is greater than equal to 0. No upper bound, nothing, right, because we are taking all solutions from the universe, because when we consider the solutions from the universe we were just putting these restrictions y1, y2, y3, y4 all were at least 0, no upper bound. This was the way universe was defined. Now we are defining a subset of the universe, which is for these variables it is only as in the universe, namely as we defined in the universe, namely they have to be at least 0, that is all. But this first variable has to be at least 5. How will we calculate that? That is easy, because we will usually define a new variable corresponding to Z1, namely y1 minus 5. Then what happens is, now we will be looking for the solutions of Z1 plus Z2 plus Z3 plus Z5, Z4 equal to 16, where this Z2 is only y2, Z3 is also y3, there is no change here, Z4 is y4, but this one is y1 minus 5, y1 minus 5. And of course the range here, this restriction, because we are for any value of y1 we are taking Z1 as y1 minus 5. The restriction on Z1 is again just that it is greater than equal to 0 like others, right, because y1 was at least 5, so it is allowed to take value 5 or more. So now Z1 is allowed to take value 0 or more, right. So now the only thing is here it won't be 16. Why? Because y1 minus 5 means when you get a solution of y1 plus y2 plus y3 plus y4 which adds up to 16, and now we are also putting a minus 5 here, so it has to be 16 minus 5, this will correspond to 11, right. So now the solution of this is the condition, these are the condition now, Z2, Z3, Z4 all has to be greater than equal to 0, this is the condition. Now we know the solution for this thing, we can use the formula r plus k minus 1, choose r being 11, k being 4 type of things, minus 1, choose 11. That means 11 plus 3, 14, choose 11, that is the solution, right, 14, choose 11. So we see that the cardinality of A1 is 14, choose 11. Now similarly we can define A2, namely the set of solutions from the universe which has the undesirable property P2, namely y2 is greater than equal to 7, y2 is greater than equal to 7. And this is also we can easily solve by converting this y1 plus y2 plus y3 plus y4 equal to 16 equation to corresponding Z1 plus Z2 plus Z3 plus Z4 equal to, for here y1 and Z1 are equal, this is equal, but here we will define Z2 as y2 minus 7, that is the only difference. Here y2 will be defined as y2 minus 7. So that means correspondingly this will become 9. This will become 9 because we are minusing 7 from this thing. When you add up to 16, this has to add up to 9. And the range of all Zi's is now greater than 0, right, because this was the only condition we had to deal with. So we minused it, then Z2 also is now greater than equal to 0, satisfying that, right. Now we can apply our known formula, namely r plus k minus 1, choose r, where r is equal to 9 and k is equal to 4, and right, that is 12. So that means cardinality of A2 is equal to 12 choose 9. Similarly, we can deal with the third property and the fourth property also, right. Let us not waste time repeating the same thing. Now the thing we have to worry about is, of course, we have to worry about how do we find something like intersection of AI and AJ. This also one example we can show. For instance, A1 intersection A2, how will you find? What is A1? A1 means our Y1, the set of solutions from the universe where Y1 is greater than equal to 5 and A2 is when Y2 is greater than equal to 7, right. Here we need both of them, no problem. When we will convert this Y1 plus Y2 plus Y3 plus Y4 is equal to 16, this equation to as before Z1 plus Z2 plus Z3 plus Z4 equal to something. What is this something, right? Here Y3 and Z3 will be equal. I will put right, this and this will be equal, while here this one we have to define as Z1 we have to define as Y1 minus 5, because this is at least 5, we want to bring Z1 to be at least 0. So that means Y1 minus 5. Similarly, Z2 we have to define as Y2 minus 7, and this will become 16 minus 5 will make it 11 and another minus 7 will make it 4, right. This will be 4, and R is equal to 4 now, because we know how to solve this equation. R equal to 4 and K equal to 4, we get this is 4 plus 4 minus 1 choose 4, namely 7 choose 4, right. Similarly, we can find, this is the same technique for each of the other things, right. So for instance, in the next case, suppose when we want to find A1 intersection A2 intersection A3, right, or maybe we can consider for a change, yeah, A3. So that means our condition here is that the undesirable properties is this 3, 5, 7 and 6. Corresponding sets will be, Z1 will be defined as Y1 minus 5, Z2 will be defined as Y2 minus 7, right. Z3 will be defined as Y3 minus 6. So and then Z4 will be Y4, right, and the corresponding sum sigma Yi was 16 here and sigma Zi will be what, because we have to minus 18 or so, this will be minus 2, right, but we know that this is not going to happen. So the solution will be 0, right. So there in that case we can apply our knowledge that now all Zi's are positive, and it's an infeasible thing we are asking for, because this is if these things are defined, then Yi's are adding up to 16, then these things should add up to 16 minus 5 is 11 minus is, so minus 4 minus 6 will minus 2, right. This is what we will get. But then we know that if each Zi is greater than equal to 0, by adding the Zi's we cannot get minus I. So the solution, set of solutions will have only cardinality 0. So 3 things taken together, so definitely you can say other 3 things also will lead to the same thing, they are going to give us 0, or the cardinality of the solution. 4 things taken together will be similarly so. So now we can apply the inclusion-exclusion principle, namely the final cardinality of this thing will be U minus sigma cardinality of AI. We have shown how to find this thing, plus sigma for every I and j, we have to add up AI intersection AJ's cardinality, and minus sigma for every I, j, k, we have to add up the cardinality of AI intersection AJ intersection AK, and this, as we have seen, every time is becoming 0, right, and plus, and this also will become, these terms will go away, is what we are told. And here we have a simpler formula here. It's simplifying, right, because the terms which are coming a little later in this sequence are all zeros, as we can easily figure out from the so, and we have already calculated these things and these things, so we can find out. Now, so that is enough for that. This is okay, general how to solve this for the number of solutions. I mean, not solve, when we want to find the number of solutions for that kind of equations with several possible conditions on the variables, right. Now, let us look at a more important problem now, namely counting the number of onto functions from an m element set to an n element set, where m is greater than or equal to n. What are these onto functions? So, as I have already told in the beginning, I am not defining functions and things like that. I assume that students are aware of what functions are and things like that. But quickly recap. So, this is A, this is B. When I say onto function, I mean that for each member of B, right, we have a pre-image. This is onto function from A to B. So, it is not function, we have a pre-image, right. It is not that there is some element which did not get a pre-image, which is so there will not be no x element of B such that right. So, if we consider the set of f of x's, x element of alright, so maybe f of y's, y element of A, this x will not be in this thing, right. There will be a pre-image for x in this. So, this is what is onto function, and and we know what is an into function. Into function means for two elements on the A side, if you take two elements on the A side, we will they will not have the same image. For instance, this is x, this is y. We will not have f of x equal to f of y. This is what into function means. When a function is into as well as onto, then what we can say is, so every member of B has a pre-image, and that is a unique pre-image in the sense that no two are coming to the same. So, for instance, the pre-image will not be more than once, there will be one, there will be more. So, which means that the cardinality of A equal to cardinality of B, and of course, I hope you know all these things. So, we are talking about the situation of onto functions, then it is clear that if it is an onto function, there should be at least the number of elements in A should be at least the number of elements in B, because if every member of B gets a pre-image, there should be at least as many members in A as there are in B. Otherwise, so the maximum number of images, members in the image, right. So, for instance, if you count this set x element of A, cardinality, this can be at most A, right, because for each element of A we are getting one this thing. So, for instance, if it was not an into function, it is possible that two different members of A can have same value of the function, then this will be even less than A, right. But if it is an onto function, this will be equal to A, right. If it is an into function, this will be equal to A. If it is onto function, we know that this has to be right, every member of B, this has to be at least B, right, every member of B has got one pre-image. Actually this is B. This is B is what we told, right, if every member has got one, right, if it is an onto function. So when it is an onto and into function, then B equal to A is what we told. Now we want to count how many onto functions can be there from A to B. So let's assume that the cardinality of A equal to M, the cardinality of B is equal to N. If you were just asking the number of functions, we all know that it is n to the power m, the number of functions. Why? Because you can take a member of x, you take say x1, x2, xm be a, right, let a be x1 and x2m, then f of x1. So this can be any of the n values in B. So there are n possible ways to assign values to f of x1. Similarly, f of x2, you can assign this value in n possible ways, any of the B values, because we are not restricting that once a value is taken, that value should not be taken. We are not saying that it should be an into function or something like that, right. There is nothing like that. So therefore we do have, so here there is n choice, here there is n choice, for this n choice, for this n choice, for this means for deciding f of xm we have n choice. So n to the power m is the number of functions, n to the power m is the number of functions. Total number of functions. And of course we can ask how many, so of course this is another way of saying it is, so this is you know, the positions of A, the members of A, we can write it as here x1, x2, x3, x4, right. So the xm, and we are assigning the members of B can be thought of as some letters. We are making m length strings, right, using alphabet from B being the alphabet, right, set of letters, right. We fill something here, fill something here, we do not have any constraint here, so we can fill it in B ways, cardinality of B ways, that means n here, n ways, that is why it is n to the power m, right. Now let us look at the number of into functions. Just this is also easy, number of into functions. Note that when it is number of into functions, the condition is that the cardinality of B has to be greater than or equal to A, the other way, right. In the case of number of onto functions, we wanted the cardinality of A to be less than or equal to the cardinality of B, but here into functions means, you know, any two things should go to two different things in, I mean they should be mapped to two different things in B. So it is very clear that like here on this B side there should be at least as many things as there are on the A sides, otherwise we cannot assign separate things, values for different values here, right. And it is okay, f of x1 you can assign in n possible ways because there are n things here, and f of x2 we can now assign in n minus 1 possible ways, because once we assign a certain things to x1 we cannot use the same thing now for x2, right. That is the property of into, right, that is what the into demands, into property demands. Similarly f of x3 can now be given only n minus 2 values. So naturally this is n into n minus 1 into up to finally n minus m plus 1, which is, you know, n m following factorial or n pm, right. This is what the number of into functions, but both this counting, the number of functions and number of into functions are easier than number of onto functions. Now we look at the more difficult problem, namely number of onto functions. As we told, we are assuming that now cardinality of A equal to M greater than or equal to N the cardinality of B. Otherwise onto it cannot, we cannot have onto functions, otherwise it is 0 when M is less than N, the number of onto functions from A to B is 0. Right. So now to find the number of onto functions, what we do is we define U, the universe, as the set of all functions. We are planning to use the inclusion-exclusion principle. So we need the universe set of all functions from A to B. We have already seen that the cardinality of the universe then is n to the power m. Now when we consider onto functions, what are the desirable properties? So this being A and this being B, say the members of B, maybe for the time being let's take B is equal to n. So this is 1, 2, 3, 4 up to n. So for instance, we can, one of the desirable properties that a function is such that 1 does not have any preimage, that means this 1 does not have any preimage here, right. So the undesirable property P1 we can define as this, 1 in B does not have any preimage. Similarly, P2 can be defined as 2. This is an undesirable property. 2 element of B does not have preimage. And similarly, the ith undesirable property, namely I element of B, does not have any preimage. It is very clear how we decided these undesirable properties. So finally we have a Pn, the n element of B, right, does not have any preimage. Because if a particular member of B does not have a preimage, then the function we are talking about is not an onto function. So therefore it is simple enough to decide these undesirable properties. And the thing we want to count, namely the number of onto functions, is clearly so for instance if we define AI as the set of functions from A to B such that it has the undesirable property Pi, namely this is a set of functions such that I element of B does not have a preimage. And clearly we are counting this one, A1 complement intersection A2 complement intersection AN complement. So this is AN complement, right, because here this means the functions which in which one has a preimage, right. This complement means the functions in which one has a preimage, the functions in which 2 has a preimage, and the functions in which n has a preimage. So when you take the intersection, the functions in which each of 1, 2, 3 up to n has a preimage, right. This is what we are interested. This is by inclusion exclusion is U minus sigma AI for I equal to 1 to n plus for every pair ij if you consider AI intersection aj and so on, right, plus till the last minus 1 raised to n. So you have to consider the intersections A1 to AN cardinality, So, but we can use the simplified formula. Why? Because if you look at the pattern, for instance, what about AI? What is the cardinality of AI? The cardinality of AI is, I mean the AI says it is a function, we are counting the number of functions such that I does not have a preimage, means no value, no member of A is such that f of x equal to I. That means it is as good as defining function from A to B bar I, right. And number of functions here only we are talking about, that is n minus 1 is the cardinality of this set. So, therefore, the number of functions is n minus 1 raised to m. So, n minus 1 raised to m, n minus 1 raised to m. And we know that which I is unimportant, because for any AI this is the number, right, number of functions, whether it is A1 or A2 or A3 or whatever. So, we can take this as alpha, the cardinality of AI. This is a common cardinality for each AI. Cardinality of AI is equal to n minus 1 raised to m. Similarly, if you want to find AI intersection AJ cardinality, here also it does not matter which I and j I take. This is again alpha 2. Why it does not take? Because there is the same value. Because here we say we are interested in those the number of functions from A to B such that number of functions from A to B such that neither I nor j has a preimage. That means there is no member in X such that f of x equal to I. Similarly, no member in A such that f of x, no member x in A such that f of x equal to j. So, it is as before, we can say that it is as good as defining a function from A to B bar I comma j, I and j are removed from B. And this we know, because here the cardinality of this set is n minus 2 and the number of such functions is n minus 2 to the power m. So, we can say that this is alpha 2 because it does not depend on I and j. As long as there are we are taking two of those sets and taking the intersection, the cardinality is going to be n minus 2 raised to m, because we are telling that the given two elements are not appearing as images of the images at all. That means they do not have preimages. Similarly, for instance, three things if you want to consider, for instance, AI intersection AJ intersection AK, it is very clear that now three things are not getting preimage. So, we are defining, we can as well think that we are defining functions, we are counting functions from A to B minus I comma j comma k. So, that means there are n minus 3 possible values, and n minus 3 to the power m is the total number of functions. And in general, when we are considering say a I1 intersection, a I2 intersection, a I t, this cardinality will be this t things, right, n minus t to the power m as we wanted. So, therefore, the number of onto functions from A to B now can be found by the inclusion exclusion principle by this thing. So, if you call this as alpha 0, so this is n choose 1, because n being the cardinality of B, right, alpha 1 plus n choose 2 alpha 2 minus n choose 3 alpha 3 and minus 1 raised to n choose n alpha n. This is what we can see. This is what n raised to m. This is what n into n minus 1 raised to m, and this is what n choose 2 n choose 2 into n minus 2 raised to m, and finally minus 1 raised to n choose n into n minus n raised to m, which is 0 raised to m. That is clear. For instance, if all the n elements in B says B are such that they don't have a pre-image, there are no such functions, because the members of A has to get mapped to something in B, right. So therefore this last term is going to be 0 clearly. So but anyway, n minus n raised to m, we are writing it, right. This is the number of onto functions. Of course, if you, this is just a formula, if you want the values, we have to evaluate it by putting the value of n and m. So but of course, so it's useful enough, we can, when we really need it, we can compute it. Another thing we should consider, two special cases we can consider here, namely when n equal to m, what is the situation? When n equal to m, we know that, as we have discussed, the number of onto functions is actually the number of bijections, right. Why? Because if it's onto, every member of B has a pre-image. So that means no two members of the A side can get mapped to the same member in B. Why is it so? Because if two members in A got mapped to the same member in B, now you know this number of members here is only equal to the number of members in B. If two of them got mapped to the same person here, then definitely the total images we see here, total the function values, if you count, right, that will be strictly less than the cardinality of this thing, the cardinality of this thing, that means the cardinality of this thing, because these are equal, right. That means it won't be onto. There will be some value here which will not get a pre-image, because we unnecessarily right, we didn't use the resources properly. If they are exactly equal means we should have mapped 1 for 1, right. So there will be one left here, so that means it won't be an onto function. So when m equal to n and the function is onto, we can also infer that it is into, that means it is onto and into together, that means bijection. And we know when m equal to n, the number of bijections from A to B, right, from n to n, right, that is n factorial, that is n factorial equal to m factorial, right. So that means this formula we wrote, sigma n choose 0 into n choose I, n minus I raised to m, this is the way I can write it for 0 to m, right, with minus 1 raised to I. So when I equal to 0, that is n choose 0, namely 1 into n raised to m itself. When I was equal to 1, that is n into n choose 1 into n minus 1 raised to m, it's a negative thing, and so on. This will become n factorial if n equal to m. This is what we told. Now the same situation we can consider what will happen if m was less than n. Then definitely we cannot have an onto function, right, because the number of members in A is strictly less than the number of members in B. How can every member in B get a pre-image? So the number of onto functions has to be 0, but this formula still works, right. So this is n choose I into n minus I raised to m minus 1 raised to I, right, I equal to 0 to n. This has to evaluate to 0 somehow. So that is what that is two special cases. So we can think. So one can try to come up. So one can try to see whether one can. This is kind of a combinatorial proof we have shown that this from when m is less than n, this will add up to 0. So by manipulating the terms, can you get this same result that you can try. Now we will look at, so we have already discussed the onto functions. Now we will look at another problem. So So, this is also a very interesting and important question. There is something called Euler's phi function, right. What is a Euler's phi function? So, we have to remember something from elementary number theory. So, one thing is the notion of relatively prime. So, when do we say two numbers I and j are relatively prime or co-prime to each other, relatively prime. So, that is when GCD of I comma j equal to 1. So, that for instance 3 and 7 they are relatively prime because GCD of 3 comma 7 is 1, or 10 and 21, yeah, GCD of 10 and 21 is 1. So, they do not have any common factors other than 1, that is what it says, right. This is relatively prime. So, one parameter which is interesting in number theory is the number of, so for given n, how many numbers are there from 1 to n minus 1 which are relatively prime to n. For instance, for 1 it is 1 itself. Sorry, so we will say greater than 1. So, from 1 to n we will consider. For numbers n greater than equal to 2 we will consider, and yeah, for 2 1 is relatively prime to 2. So, it is equal to 1 only. For 3, so we this number of numbers from 1 to n minus 1 which is relatively prime to n here. So, below n less, or we can even say less than equal to n because n anyway is not going to be relatively prime. So, that is denoted by phi of n. This is the Euler's phi function, right. So, phi of 2 is equal to 1 and phi of 3 is equal to 2. Why? Because 1 is relatively prime, 2 is also relatively prime to 3. And what is phi of 4? Phi of 4 is equal to 1 is relatively prime, 2 is not relatively prime, but 3 is relatively prime. This is 2. So, phi of 5 is 4, 1, 2, 3, 4, and phi of 6 is what? Phi of 6 is 1 is 2 is not, 3 is 4 is not, right, 5 is 1, 2, 3, right. So, like that. So, now we can look at more general cases. For instance, what about phi of a prime number p? It is very easy to see that it is p minus 1 because all the numbers below p from 1 to p minus 1 will be relatively prime to p, p being a prime number, right. There is nothing common, like no common factor will be there between p and a number between 1 to p minus 1. Phi of p is p minus 1. And now we want to derive a general formula for phi of n when n equal to p1 raised to e1, p2 raised to e2, say pk raised to ek, right. This is what we want. We will show that this is equal to n into product of I equal to 1 to k 1 minus 1 by pi. For instance, you can put suppose it was just a prime number, that means E1 P1 is equal to P, E1 is equal to 1, and yeah, so that is what. So, that k equal to 1 case. In that case you can see that phi of n is equal to n into, n here is p into product of I equal to 1 to 1, right, only one term will be there, 1 minus 1 by p. What is this? So, then we do not have to put the product at all, right. So, this is p into 1 minus p by p, which is 1 minus p, as we have seen before, right. So, similarly, yeah, so we can do the calculation and find out. For instance, what is for 6 equal to 2 into 3. So, E1 and E2 both are 1 here. So then yeah, phi of 6 is equal to 6 into this is what 2 1 minus 1 by 2 into 1 minus 1 by 3, right. So this is 6 into, so 2 minus 1, that is 1 by 2, this is 2 by 3. So we get 2. So what was 6? 1, 2, 3, 4, 5, 6. Yeah, correct. So I wrote it wrongly before, it is 2. So this 2 is not relatively prime, 3 is not relatively prime, 4 is not relatively prime. So 1 and 5 are the relatively prime numbers to 6. So 2 is the answer. So we get 2. So earlier I had written, yeah, 5. This is wrong. So this is 2. I think I thought 3 also is relatively prime to 6. That is mistake of case. So yeah, this is 2. Okay, anyway, so this is the formula. So we want to derive this formula using inclusion-exclusion principle. The technique is very similar. What we do is we will take n minus 1 as the universe. N minus 1 means from 1 to n minus 1, and then we define the undesirable properties. What are the undesirable properties? So because our n is p1 raised to e1, p2 raised to e2, some pk raised to ek. So undesirable means a given k in the universe, given k in the universe, that is not relatively prime to n. This is undesirable, right? Why is it not relatively prime? There is some common factor, and if there is some common factor, there is one of these p1 or p2 or pk as a common factor, right? If there is a common factor, there is a common prime factor, right? So it's either p1 or p2 or pk. So we can define the property, undesirable property. So here I have used p1, p2, etc. for undesirable properties. So let's say h1 is the first undesirable property, that is p1 divides k. Of course p1 divides n. If p1 divides k also, then p1 is a common factor for n and k. So this is indeed an undesirable property. Similarly h2 would mean p2 divides k, and similarly hi would mean, right, pi, the ith prime number, divides k. The properties are defined for hi of k, that is what divides k, right. K has the property hi is what we are saying. So like that we can define, oh sorry, so I goofed up by saying that this k, I should have taken a different name for the number. Maybe we will take m for the number, p divides m, because k I am using for the number of prime numbers here. So this was k. So this, let's say m. So we say h1 of m, h2 of m, these are the undesirable properties. Now we also define ai is the set of numbers from the universe, right, 1 to n minus 1, the numbers from 1 to n minus 1, such that it has property hi. So we will continue in the next class.